Okay, so this handout is Unit 8A, which is the intro to our unit that deals primarily with right triangles. And so we're going to start with this shape that's over on the right. And in it, the first question is why? Oh, and the big shape you can tell is a square because every side is the same. They're all A plus B. So all four sides are the same. And all the angles in the big shape are right angles, so that's what you need to be a square. Four right angles, four congruent sides. So one of the questions about the big square is why are the four triangles that are around the sides, so this guy here, this guy here, this guy here, this guy there, why are they all congruent to each other? Well, if you look at every one of those triangles, they all have the short side A, the long side B, and a right angle in between. So all four triangles are congruent because of SAS, right? We have SAS for all four triangles. So that's why the four triangles are congruent. Next question is why does the shape in the center have to also be a square? Um, well, so we need four right angles and four congruent sides. The congruent sides we can get because since we know all four triangles are congruent, we know that these sides all have to match up because of CPCTC. So the sides of the square in the center are all congruent because the triangles are all congruent. So what we're really doing is we're saying corresponding parts of congruent triangles are congruent. So this is four congruent sides. And then we need to figure out why these angles are right angles. So the way that we can do that, so first let me mark this. These are all congruent. Okay, the way to check that the angles are all the same, or that they're right angles, is let's look at the slope of this thing. Right? Now the nice thing is there's already a slope triangle built around it right here. I went up B units and over A units. So this guy's slope is rise over run B over A. If you look at this guy's slope over here, well, the rise is B and the run is A also, so this guy's slope is also B over A. This slope, though, this one's going downhill, and the rise is an A in this case, and the run is a B, and since it's downhill, it's negative, and so it's A over B. And then you can do the same thing down here with this one. This slope is going to be negative A over B. And then if you notice, these two slopes, A over B or B over A and negative A over B, they're negative reciprocals. So this is a right angle. And if you look at these two slopes, same deal, negative reciprocal slopes, right angle. These two slopes, negative reciprocals, so right angle. And the same deal here, negative reciprocals, right angle. So since the slopes of, let's say, adjacent sides are negative reciprocals, all adjacent sides of the square, adjacent sides are perpendicular. And so then that's how we get four right angles. So we got four congruent sides and four congruent angles. And so from these two things put together, we know that the center is a square. Okay. So let me clear off this picture, and then we'll answer the last thing. So the last thing says to find the area of the large square two different ways. So one way, let me just draw the square by itself here. We know that each side is A plus B, B plus A plus B, B plus A. They're all A plus B. And the area of a square is going to be length times width, which is really a plus b squared, which if we work that out a little bit, you'd have to FOIL it. So it's a plus b times a plus b, which ends up being a squared plus ab plus ba plus b squared. So that comes out to a squared plus 2ab, because these guys are really both ab, plus b squared. Okay, so that's one way of finding the area of the square. So let me put that in a box right there. The other way that we can use is to actually add up each part of this individually. So it'd be like adding up just this, plus just this, plus just this, plus just this, and then throwing in that area in the middle. So let's call the middle something, the sides of the square in the middle something. So we'll call these sides C right there, so that we can actually, oh, and I'll put in the right angles too, so we can actually add in that area. So first we need 4 triangle areas. So the area of the square is also going to be equal to the area of the 4 triangles plus the area of the center square, let's say. Well, okay, so the 4 triangles, I'll draw one of them right here. So the 4 triangles all look like this. A is the short side, B is the long side, and they're a right triangle. So the area of a triangle is 1/2 base height, and in this case, it's 1/2 A times B, right? So 4 of them, it's going to be 4 times 1/2 AB. And then we got the center square, and since we've called the side C there, it's going to be C times C, so C squared. So this is going to turn into 2, because it's 4 times 1/2, which is 2, AB, plus C squared. So there's the other area of the square. And they're the same square, so you know that this area term right here is the same as that area term right there. Okay, and that's what we're going to try and figure out in D. We know that if this is the area of the whole square and this is the area of the whole square, then they must be the same. So I'll write it like this. Area of the square must equal area of the square. So a squared plus 2ab plus b squared has to equal the other area, 2ab plus c squared. And if you notice, the two ABs are going to cancel each other, and you're left with a squared plus b squared has to equal c squared. And if you look at any one of those triangles in the original picture, A and B are the sides of the right triangle, and C is the hypotenuse, right? A and B, sides of the right triangle, C is the hypotenuse, a squared plus b squared equals c squared. Now, if you actually look at what we've done all the way through this problem, we never actually used the Pythagorean theorem anywhere, but we ended up with it. So this thing right here, this problem, number 1, is a proof of the Pythagorean theorem. We proved it the other day using similar triangles. Now we're proving it using actually congruent triangles and chopping up a square a certain way. Okay. So let's take a look at some problems that come after this. All right, back to our typical 3 triangle right angle chopped sort of problem. Okay, so we got 3 right triangles. They're all similar to each other. Name the ones that are similar to ABC. So in this one, let's draw them by themselves. So here's the big triangle with the right angle. Here's A, here's B, here's C. And then the 2 smaller ones look like this. This one is A, D, B. Okay. Sorry if you just heard some muffled noise. My cat keeps rubbing up against the laptop here, and I think she's brushing against the microphone. So the last triangle looks like this. And this one, BD is the altitude and DC is the base. Okay, so then what we can do, you don't want to just base it on what the triangles look like. You might be able to tell if you rotate this last triangle 90 degrees, it'll look like the triangle next to it. So that one's not too bad to eyeball. But the way to do this where you know you're not going to mess up is by using reflexive angles. So if you find like angle A, well, here's an angle A, and there's the same angle A. And then if we found angle C, well, here's angle C, so I'll put two curves. And here's angle C, so I'm going to put two curves there. And now if you look at the three small triangles that we've drawn, well, ABC has all three angles marked, whereas ABD doesn't, and the one type of angle that it's missing is a two curve. And in the last triangle, the only thing that this angle is missing is a one curve. So now we can match stuff up. ABC goes one curve, right angle, two curves. So then I just have to make sure I do the same thing. So one angle, right angle, one curve, right angle, two curves is ADB. And then if I do the same thing for the third triangle, one angle, right angle, two curves. One curve, right angle, two curves, BDC. And it says use part A to set up some proportions. Okay, so there are a bunch of different proportions you can set up. We did some last class with some various things, but let me color code the sides here. So I'll mark all the hypotenuses in red. Because you know the long sides will have to go together. I'll mark the shortest side. So between the right angle and the one curve, I'll mark those in green here. And then this one. And then the last ones I'll just do in blue and kind of zigzag this. So this goes with this, which goes with that. Okay, so the way I'm going to set up some, let's see here. Let's go, I don't know, I'm going to make something up. Let's try AD over BD equals. So there are different ways you could think about this. You might notice that AD and BD both come out of this triangle in the middle, and it'd be the green over the blue. So as long as you match it up with the green over blue, you're guaranteed to be right. So green over blue would be like BD over DC in this triangle. And green over blue here would be AB over BC. Right. Let's set up one other one, for example. So let's try like AB over AC. So AB over AC would be, they all come out of the first triangle and it's green over red. So then we can set up green over red everywhere. So AD over AB. Or let's see, what did I say? It was green over red. So BD over BC. Okay, now it turns out there's one theorem that I found comes in really handy for a lot of students when they're solving problems that use this diagram, which is surprisingly common in this unit. So this is it right here. This guy. AD over BD equals BD over DC. So I'm going to write it right here. AD over BD equals BD over DC. And over the years, I've had a lot of different students call this thing what they call the up-down theorem. That's not a technical term, by the way. What it is, the reason that they nicknamed it DAD, AD over BD, if you look at this picture, AD is here, and then BD is here, so it's kind of like going up. And then the second ratio that you're setting it equal to is BD over DC, so you come back down, BD over DC, so you do that. So you go up, and then you come back down. So that's why. And remember, the key here is you have to have a right angle there. But you go up, come back down. So if this was little a, little b, little c, you'd be setting up a over b equals b over c. Okay? Oh, this is a typo. That should say number 3. Okay, so let's take a look at 3. Solve for x, y, and z. Well, notice we got the right angle at the top, and we got the right angle, the triangle is chopped from the right angle into 2 smaller right triangles. So we can use the up-down theorem here. 3 over x equals x over 10. So 3 over x equals x over 10. And if we cross multiply, we'll get 30 equals x squared. So then root 30 equals x. If you wanted to simplify that root, you're trying to find things that have to go into it. Let's see, does anything go in? This would be root 6 times root 5, which is root 2 times root 3 times root 5. There are no pairs there, so root 30 is actually as simple as it gets. So this one, x is root 30. Okay, now we have to solve for y. So notice if I draw the triangle over here on the side by itself, this is 3. We now know that this is root 30, and here's y. So I can do Pythag on just that little right triangle. So 3 squared plus root 30 squared equals y squared. 3 squared is 9. 30 squared, root 30 squared is 30 equals y squared. So this is going to be 39 equals y, or root 39 equals y. And then z, we can do the same sort of thing on this triangle. This is 10, this is root 30, this is z. So we got root 30 squared plus 10 squared equals z squared. Root 30 squared is 30, 10 squared is 100 equals z squared. So we're going to get 130, and then we got to take the square root. So this is root 130. Okay. Let's take a look at what comes next. Let's see. To find the height of a tree, Amanda uses a book, which has a right angle. So that's kind of the key to the problem. She positions the book near her eye. So let's draw a picture here. So we got the ground, and here's the tree right here. Okay. And let's see here. She positions the book near her eye so the top and bottom of the tree are in line with the cover's edges. So basically she's standing there. Let's see, how do I want to do this? Let's try this. Okay, so the idea is she's holding the book right here, and the book is key because it's got right angles as the edges. So this guy is the book, let's say. But the key is it's got a right angle there. And she's holding the book so that if her eye is right there, then the top of the book lines up directly, that line of sight goes straight to the top of the tree, and the bottom of the book leads her to look right at the bottom of the tree. And we'll draw her. So here she is. There. Whoop. Okay. Yeah, that's about as good as it's going to get. Oh, well, okay, we'll add that. All right. So, let's see here. What do we know? So this is definitely not the scale, by the way. That tree would not be very big. So her eyes are 5 feet from the ground. So this length is 5 feet. And she's 14 feet away from the tree. And it turns out that's all you need, along with the fact that the book has a right angle, to figure out how tall the tree is. So here's kind of the key to the problem. Now, the thing that we've been studying is that up, down, you got a right triangle chopped into two other right triangles. Well, here's a right triangle. And if I chop it from the right, and notice in all of these problems up here, the two small right triangles are made by cutting from the right angle straight down to the other side. So in this problem, I'm going to have to cut straight across like that. Right? Now, we can label some sides here. We actually know that this is going to have to be 14 feet because this was 14 feet. And we know that this part of the tree right here is going to be 5 feet because that's her eye level right there. If we knew this part of the tree, then I could just add it to 5 and know how tall the whole tree is. Well, we can do that because if you look at it, here's the problem we're looking at. 14 here, 5 here, x here, with right angles there. So we can actually use that up-down theorem, where if you turn this thing sideways, you can tell it's going to be 5 over 14 equals 14 over x. So let's set that up. And then if you cross multiply, you get 5x equals 14 squared, which is 196. And then x ends up being 196 divided by 5, which is 39.2. So it's 39.2. Oh, wait. That's not right. The x is right. It is 39.2. But if you notice, the tree isn't 39.2 feet tall. It's 39.2 plus 5 feet tall. So that ends up being 44.2. So we're 44.2 feet tall. Okay. Let's see. Let's keep going here. Solve for x, y, and z in this diagram. Okay, well, it's another big right triangle chopped from the right angle into two smaller right triangles. Okay, well, that means that we can use some ratios that we've set up before. And one of the ratios, if we did the up-down theorem, it would be x over 12 equals 12 over x plus 7. Right? You're always going from that main hypotenuse, by the way. So x over 12 equals 12 over x plus 7. Well, this one we can solve because it's only got x terms and constants. So I've got 12 squared is 144 equals, and then x times x plus 7. So x times x plus 7. So that would be 144 equals x squared plus 7x. And then if I bring the 144 over, then let's see. You could factor that if you wanted, or you could do quadratic formula. I'll do the quadratic formula. C is negative 144. So then if we plug that into the quad form, x equals negative b plus or minus square root b squared minus 4ac all over 2a. Here, we'll just do it real quick. Whoop. All right. So let's see. A is 1, so I'm going to do 1, store as alpha a. B is 7, so 7, store as alpha b. Oops. 7, store alpha b. And then C is negative 144. Store it as C. And then to get the fraction, it's alpha f1. Fraction numerator over denominator. And it's going to be negative b. We'll do plus first. The square root b squared minus 4ac all over 2a. Enter. So one of the answers is 9. And the other answer, I'll just come back up here, cut and paste, and then scroll back over to the plus sign and change that to a minus. And we get negative 16. So there are two answers for x, but notice x is a side length right here. Whoa, hold on. Okay, sorry about that. I think the screen should be good now. So x is a side length here, so negative 16 is not going to work for that. So we're going to choose the one that's 9 and cross off the negative 16. So x is 9, which actually makes this part 9 plus 7 is, this one will be 16 right here. Okay, so now we got to solve for y and z. X is 9. So let's look at this. Right there, we've got this side's 9, this side's 12, this side's y, and it's a right triangle. Right? Whoops. I don't know why I'm drawing it that way. 9, 12, and y. So if we do Python on this, it's 9 squared plus 12 squared equals y squared. So that's 81 plus 144 equals y squared. That's going to be 225 is y squared. And then if you take the square root, you actually get just 15. And then z squared, or z, we can do using Python again. So 12 squared plus 16 squared is going to be z squared in this case. You could use similar triangles if you wanted, but this is just as easy. So it's 144 plus 256 equals z squared. So that's going to come out to 400 even is z squared. And then if you take the square root, you get 20. So z is 20. Okay. I think that's the end. Yeah. So hopefully that makes sense. It's we proved Pythag, we used it in a few different ways, and we also learned a new theorem that you can use. So, all right, hope that helps.